Let's look at another way to calculate the instantaneous rate of change, also known as the slope of the tangent, to a function, right? And this time we're going to actually be calculating the equation of the tangent for any function, right, for a particular function, and we're going to be using something called the first principle method, right? So the first principle method is written as f prime of x is equal to limit as h approaches 0, f of x plus h minus f of x over h. Okay? Now the f prime of x actually refers to the equation of the slope of the tangent, right? So the slope of the tangent we know is the instantaneous rate of change. So we can actually figure out the instantaneous rate of change using this equation at any point of x, right? So this is going to be pretty useful, especially when we're looking at instantaneous rate of changes. Now, in this case, this limit here, h approaches 0, if we look at this rational function, right, this rational equation really, if we look at this rational expression, we can see that when h approaches 0, when it gets closer and closer to 0, the denominator will become 0, and this whole rational expression becomes undefined, right? So we clearly don't want that. So we need a way to kind of get rid of this h on the denominator. So I'm going to show you how to do that. So first I'm going to look at this f of x plus h term. In this case, f of x is 3x squared minus 4. So if I plug this in, I get 3 times x plus h squared minus 4. Now, you could use FOIL method to kind of expand this out. I think it's a little tedious, so I'm just going to use this template, a plus b squared. You get a squared plus 2ab plus b squared. I'm going to apply this template to the x plus h squared, right? In this case, x is a and h is b. And in this case, what you get here is 3 times a squared, which is x squared, plus 2ab, which is 2xh, plus h squared, which is b squared, minus 4. So it's a lot faster that way. I'm going to FOIL this out. Okay, so if I FOIL this out, expand this, and you get 3x squared plus 6xh plus 3h squared, right, minus 4. Okay, so this is your f of x plus h term. We also have a negative f of x term, which is basically negative 3x squared minus 4, which is negative 3x squared plus 4. And I'm going to combine my f of x plus h term with my negative f of x term. So that's going to look like 3x squared plus 6xh plus 3h squared minus 4 minus 3x squared plus 4. Okay? You can notice here that the like terms are equal but opposite signs, and they cancel out, right? So if you collect them, they'll cancel out. And the numerator is just left with 6xh plus 3h squared. Now you can notice here that h is a common factor. So I'm going to factor out my common factor, which is h. You get 6x plus 3h. Okay? Now this was the numerator. Now if I put this back into my equation, f prime of x is equal to limit as h approaches 0, f of x plus h minus f of x looks like h 6x plus 3h over h. And we said that one of our problems initially was that this h on the denominator, if it became 0, this whole rational expression basically becomes undefined, right? So, but now we can see that because we factor out an h as a common factor on the numerator, these two h's can cancel out. And now h can actually approach 0, right? So if h can approach 0, we can let h equal 0 now, and f prime of x, which is the slope of the tangent, right? Whoops, I'm just going to get rid of that little tick there. F prime of x can be equal to 6x plus 3 times 0, which is basically 6x. So the equation of the slope of the tangent is 6x. If you wanted to figure out the instantaneous rate of change at x is equal to 2, well, normally this point here is f of 2 is equal to 2 squared minus 4. So this is like 3 times 4 minus 4. This is like 8. So f of 2 is 8. So the point here is 2 and 8. So at this point, 2 and 8, the slope of the tangent, or the instantaneous rate of change here, f prime of 2 is 6 times 2, which is 12. So the instantaneous rate of change at point x is equal to 2 is 12.